Hello everybody, welcome back to another Gregorius Maths video. Today we'll be looking at path homotopy and the product of two paths. Okay, this is in preparation of hopefully tomorrow's video about the fundamental group, okay, which is very important in algebraic topology. Okay, so first, before we look at path homotopy, let's look at what a path is. Okay, a path is a continuous map F, okay, which takes you from I, the unit interval, well, the interval, okay, so the closed interval between 0 and 1, to some topological space X, such that f of 0 equals x0 and f of 1 equals x1, okay? So what it will look like is some path like this, where its starting point is x0 and its end point is x1. This is more formally known as its initial point, and this is, I think it's known as its end point. Okay? So now let's look at what it means for two paths to be homotopic to each other. So if we have a path like this, let's call it F, and we have a path here, let's call it G, okay? If the requirement that they're path homotopic is that they share the same end and initial points, okay? And the normal homotopy condition that you can continuously deform this one into that, okay? But how do we make this rigorous? Well, we make it rigorous by the following definition. Two paths, F and G, are path homotopic if, okay, there is some F, capital F, which takes you from, well, remember that normally this function would go from something cross I, okay, some topological space, say X cross I, but it would be the domain of the function, right? However, in this case, the domain of any two paths is just I, so it will go from I cross I into some topological space X, such that, well, the normal conditions of homotopy are satisfied, so capital F of S0 is equal to F of S, and capital F of S1 is equal to G of S, okay? And also the added condition that capital F of 0t is equal to x0, the initial point, and F of 1t is equal to x1, the ending point, okay? So this is basically just formalizing the intuition which I just gave, okay? Now, let's look at a quick example, namely convex sets. Okay, what is a convex set? Well, I'll just give you an example of something that's not a convex set. Okay, for example this, because if we pick this point and this point, there is no straight line segment joining them, okay, completely contained inside of this space. However, the circle, for example, is a convex set because any 2 points A and B we pick, there is a line segment joining them, okay, completely contained inside the circle, okay? And there's a general equation, okay, assuming that the two paths share ending and starting points, okay, there is a general equation called the straight-line homotopy between these two paths in the convex set. Okay, namely, it's f of st is equal to 1 minus t times f of s plus t times g of s. Okay? And what this will look like is, say we have a path here, and we have another path here. Again, they share ending and initial points. Okay? Every point we pick is joined by a line segment. Okay? So, for example, if we look at a couple of these, this point moves here via the straight line homotopy, and etc. and etc. Okay? Now let's introduce some algebra to the situation. So far we've been looking at the geometry part, the topology part of the algebraic topology. Let's introduce some algebra, namely the product. Okay? And it's defined as follows: f star g, and this might look familiar, f star g of s, for people who watched Topology 2.1, this might look familiar to you. It is, because it's pretty much the same way, the same piecewise function that we defined, let's call it h of s, to prove that the path homotopy is, that normal homotopy is an equivalence relation. Of course, you can prove it in the exact same way for path homotopy. But anyway, let's call it h of s. This is equal to f of 2s if s is between 0 and a half. Okay? And it's g of 2s minus 1 if s is between 1/2 and 1. Okay? So now, let's take a look at what's called the Homotopy classes, okay, which is just the equivalence class of f star the equivalence class of g of s. Actually, we'll just look at this for now. The equivalence class of f star, the equivalence class of g, is equal to the equivalence class of f star g. Okay, what we mean by equivalence class is basically, okay, so we've got our, well, the reason we proved that the homotopy, or in this case the path homotopy, is an equivalence relation is because now we have an equivalence relation, so the equivalence class of f is equal to the set of all g, which goes from, I don't know, some topological space x to y, such that g is path homotopic to f, or in this case, actually yeah, I will say path homotopic, and it will say from I cross I is path homotopic to f. That's the notation for path homotopic. It's just the normal notation for homotopy, except with a little p subscript. Okay? I'm sure if you go onto Wikipedia for the general definition of an equivalence class, it's pretty simple to understand. Okay? Okay. But now, remember that this isn't the only element in the equivalence class of f. Well, let's say that it isn't, okay? So this is equal to the equivalence class of some other representative, f prime, star some other equivalence class representative, g prime. But is this equal to the equivalence class of f prime star the equivalence class of g prime? I mean, are these two equal? Okay? That will show that this is well defined. Okay? Well, it turns out that this is true. Sorry, I should probably say path homotopic. Okay? Turns out that this is true via the following. Okay, if we define okay, so the equivalence class of f star g is path homotopic to the equivalence class. Actually, I'm just going to say homotopic for now. Okay, to the equivalence class of f prime star g prime. Okay, but I'm sure if, actually I will say path homotopic. Okay, as long as they share the same initial and end point, they are path homotopic. via, okay, some capital H of ST equal to capital F of 2s for s between 0 and a half, and capital G of 2s minus 1 if s is between 1/2 and 1. Okay? Why is this true? Well, it's easy to verify because remember that if we plug in a half, we get f of 1 with, f of 2s comma t, g of 2s minus 1 comma t. Okay, capital F in general was the homotopy between f and f prime, and capital G was the homotopy between g and g prime. Okay, so f of 1t is equal to x1 is equal to g of 0t. Okay, because remember that the product, well, don't remember, I'm just telling you now, that the product, geometrically speaking, is if we have a path which goes from x0 to x1, and then we have another path which goes to x2, call this path g, call this path f. F star g is when you ignore this. Middle point here is equal to that. Okay? So this should be logical now. And for now, that's it. Goodbye.